So we want to talk about two procedures that produces new groups from old ones. One is to take Cartesian products of given groups, and the other one is to take subgroup of a given group. So I want to talk about subgroups quite a bit. Let's go through the Cartesian product rather quickly. This is a simple thing. Let G and H be two groups. Then the Cartesian product G cross H, which is a set of all ordered pairs that look like this, G comma H, where G is an element of G, H is an element of H. This can be given a group structure just by defining the group operation component-wise. Forms a group with binary operation. So to define a group, you need a set. Here is a set. You need a binary operation. And here is the binary operation. You give me two things from G cross H. They look like this, G1, H1 and G2, H2. So G1, G2 came from G, and H1, H2 came from H. And to combine them, you just combine the G's using the operation of capital G, and combine the H1 and H2 using the operation of capital H. So this dot here between G1 and G2 is the group operation of G. This dot here is the group operation of capital H. And this dot on the left-hand side is the multiplication that I'm defining on G cross H. So G cross H becomes a group with binary operation defined by this, and you also need a special element called the identity. So here the E is going to be E comma E. Except this is a little confusing. These E's are different E's. This E here is the identity of the group G, and this is the identity of the group H. So if there is chance of confusion, we'll write them like this. And the E on the left-hand side is the identity of G cross H that I just defined. And what you have to do is you have to check that the group axioms hold. And that's very straightforward. We'll leave that. So we say that the group, so this is an unsaid exercise if you want. You have to verify this. What do you verify? By this I mean that does form a group, meaning the group axioms are satisfied. That the group G cross H is the direct product. That's the word that one sometimes uses. Product of G and H. Okay. And more generally, similarly define the direct product of a bunch of groups. If you give me 5 groups, I can define their direct product. At least finitely many, it's fine. You can even do direct products with infinite families, but it's a little more subtle and we won't get into it right now. And I do need one extra bit of notation. In particular, you now have groups like G cross G, which we call G square, and G cube, which is G cross G, and so on. A special case of this you might have seen if you have looked at vector spaces. It's like R2 with addition, and the 0 vector is a group, which is really nothing but, so this R2 is nothing but R cross R in the present notation. The vector addition is exactly this group operation of Cartesian product. You just add vectors component-wise, right? Except the addition on R is denoted by plus. It's not denoted by dot like up here. Yeah. More generally, the vector space Rn, if you have looked at it with addition, that group is just R cross R, n copies. So this you're familiar with. But you can now, using this, make new groups like Z mod 2 cross Z mod 2. That's a group of order 4. It has 4 things, 0, 0, 0, 1, 1, 0, 1, 1. Each element has, each non-trivial element, these 3, has order 2, you can check. And that immediately proves this is not cyclic. Yeah. Sometimes this gives you new groups, like this one is not one of the cyclic groups. But sometimes, like this one, we'll see is secretly same as Z mod 6. Not really same, but the word is isomorphic. It has the same group theoretic properties. This is within quotes. After we define homomorphism and isomorphism in the next section, we will make this precise. But the structure of Z mod 2 cross Z mod 3 is the same as the group theoretic structure of Z mod 6, for example. Okay. Now let's talk about subgroups. And this is sort of the notion that you have seen if you have any algebraic structure at all. When you have seen vector spaces, when you talk about vector spaces, you talk of subspaces. If you have looked at ring theory, if you have a ring, you have a subring. When you have a group, you have a subgroup. So here's the definition. Let G be a group, and let's write the whole triple. The composition is called dot, the identity is called E. Be a group. Let H be a subset. We say H is a subgroup if H becomes a group in its own right. Say that H is a subgroup of G if H becomes a group itself with the operation and the identity borrowed from G. So maybe for emphasis, let me call this identity of G. So this is what I mean here. And this dot is, I'll write for emphasis, group operation of G. So H with the group operation of G and the identity of G becomes a group. Or rather, E is a group, is fine. And we'll give examples, so you'll see in a second. I mean, so in words, we say that H itself is a group with the operations borrowed from G and the identity borrowed from G. So notation, I'll use, let's say H less than or equal to G means H is a subgroup of G. So this less than or equal to sign is abbreviation for is a subgroup of. Okay. Example. Maybe first couple of examples. Like Z plus 0 is a subgroup of rational numbers plus 0, is a subgroup of real number plus 0. Okay? But maybe I should emphasize that the non-zero rational numbers is not a subgroup of the rational numbers, because this is a group under multiplication. And this is a group under addition. Yeah, so when I say subgroup, you have to borrow the operation from the big group. Just being a subset is not enough. These are different operations. So this is not true. Okay? Because here, if you write the whole thing, it's really this is the group. And here, it's plus and 0. So the operation is different. The identities are different. It's definitely not a subgroup. not a subgroup. Okay. So for example, just some more simple examples. Z mod 12. Let's look at that as G. Let's look at some subgroups. If you take multiples of 2, you'll see that you get a subgroup. This is a subgroup. Because if you just look at this subset, you can check that it forms a group in its own right when you when the identity is still there, and then you can just operate on them and you'll stay in this even number set. And the inverse of each of them is also in this, so this itself forms a group. So the group laws are satisfied, of course, because the group laws are satisfied in G already. And I'll give you some more examples in a bit, but let me write down sort of the all-important more examples coming up in our next video. But let's write down this rather central recognition principle. This is how you check something is a subgroup. Let H be a subset of G. So G is a group here. Then the following are equivalent. H is a subgroup of G. B, or rather 2 maybe, is that H contains the identity of G, and if you take two things in H, then their product is in H and the inverses are in H. So if this happens, whenever A and B are in H, then A times B is in H. And by this times, I mean the group operation of G again, just for emphasis. Yeah. When this condition is satisfied, we say that H is closed under addition, under multiplication, I'm sorry. There's no addition here. And when you have this condition that whenever A is in H, A inverse in H, you say that H is closed under inverse. So we are saying that something is a subgroup if and only if it contains the identity and the subset is closed under multiplication and under taking inverse. So whenever you have two things in this subset, their product is also there and the inverse of every element is also in there. And the third one just says, it's a little bit of economy. It's almost same as 2. It sounds slightly different, but not big change. H is non-empty, and if AB is in H, then A inverse B is in H. Well, this is just, we'll see, 2 and 3 are very close to each other. 3 is just a little more convenient in some circumstances. So we'll check the proof next time.